Okay, so in this video I'm going to make a short introduction to conditional probability. So in this table I have a group of adults that was sampled and found how many are males, how many are females, and then across we have how many are left-handed and how many are right-handed. So in this table we're giving the totals here, total males and females for a total of 100, so it's all clear. Sometimes we might omit the totals, so you have to be careful about that. Okay, so in this question it says a person is chosen from this group at random. The event E is the person selected as male. F, the person selected as left-handed. Let's see, what's a probability that you selected F, a left-handed person? So left-handed, you're reading at this row. There's 20 left-handed out of the total. So it's 20 out of 100. So 0.2. Now find a probability of E, which is a person was a male. So for that, I'm looking at this here. And the males are 50, so it's 50 out of 100. So it's 1/2. This is my answer. It's very simple, just reading from the table. Now the new part is this third bullet. Find the probability that the person selected is a male given that the person is left-handed. So here the given part means we can assume that the person we selected is left-handed. Okay, so now when we do this, it's a little bit different question. Now it's asking, we can assume the person is left-handed, which means we can assume we're only talking about people in this row. That's a condition that we're assuming is true. So condition that the person was left-handed, what's the probability that the person is a male? Now you're looking at 12 males out of 20, because I'm looking at that row, not out of 100. So it's 12 out of 20. So that's 6 over 10, so 0.6. Right? Now I'm going to do it backwards. So the next question says, find the probability that the person is left-handed, given that the person is a male. So let me erase this. Now the given part, okay, this little bar here, this is how we write it. Sorry, I didn't say that. So E bar F means the probability of the first event, E, the person is a male, given that. So this part after the bar means the given part. So now I'm reading it backwards for this one. The probability of F given E means the probability that the person is left-handed, given that is a male. So the given part now is this, that it's a male. Find the probability of F, which is a person that's left-handed. So now I'm looking at 12, but divided by 50. Right? So it's 24 over 100, something like that. Okay. So are we just reading these from a table? I hope this makes sense, that we are getting these numbers from the table, and that you could have figured these things out even if I didn't tell you the notation. All we needed was to understand what this means, and that means this. Okay? So the notation I was been using is E given F, right? So that's that conditional probability. Now, when they define two events to be independent, if knowing that one happened doesn't change the probability of the other one. And that is the probability of the events E given F would be the same as the probability of E. So knowing that F happened didn't change the probability of F. Or the probability of F given E is the same as the probability of F. So knowing that E happened wouldn't have changed the probability of F. In my examples over here, E and F are not independent because, for example, P of E was 1/2, and E given F was 0.6, so it did change, right? So 0.5 to 0.6. Or you can see it the other way over. The other example, that the probability of F is 0.2 and the probability of F given E is 0.24. So they did change, so these are not independent. So two events are going to be dependent if knowing that one happened affects the probability of the other one. It's the same, but backwards. So another way of saying this is that knowing that one of them occurred does not change the probability of the other. So my silly examples here are if a person, pretend you select a person at random from the street or from a mall, and you ask them two questions. You ask them, what is the highest degree of level of education, and what is their annual income. So here the fact is that the example I'm trying to point out is that knowing that the person has a high degree of education is going to change the probability that the person makes 80,000 or more. It's not a guarantee, but it would certainly change the probability. So these events are not independent. And my second example is a car driving over 85 miles on the highway. After the event, a car gets in a car accident. So again, it's not a guarantee, but knowing that the car was driving over 85 miles per hour certainly increases the probability of the car getting in an accident. So these events are not independent. So we have a formula that for the conditional probability that this is written right here. The way to think about this is something like this. So this is going to be a circle that symbolizes the event F, this the event E. So if this is F and that is E, well, E and F is this is in symbol, this would be E intersection F, if you know set notation. So this is this. Okay, and so let's try to make sense of this. The probability of F given E means the probability that F happened knowing that E happened. And I hope to see that now this picture makes total sense, or the formula makes sense. The probability of F given E means that E already happened, so you're on this side. So what's the probability of F given that E happened? Well, it's how many you have in here, right, in the intersection in this part, divided by how many you have over here. Right, so that's exactly what this is telling you. So I hope that picture expresses how simple this formula is. Sometimes we don't relate this to what we were doing, but this is what we did in the first example with the table. Now, this way of writing it is very useful, but sometimes we use it more like it's down here, in the sense where the probability of E and F is the probability of E times the probability of F given E. So what happened here was grab this and multiply it, and now it's over here. Right? So this is the same formula, but we'll go over. So you will use this formula in the homework for sure. Okay, let me do another silly example just to clarify these things to be sure we're getting it. Suppose you roll die, and A is the event, you get any numbers between 1 and 4. B is the event, you get an even number, 2, 4, 6. Find the probability of A, given that B happened. And I'm going to just make use of this picture here. I'm not going to use a formula, because in this case, it's very, very simple. Hope you see that A given B, the probability of A given B would be, I'm going to do it like this. How about I do a circle? So what I have in my circle, I have my 2 and the 4 are the ones that are in common, right? I have the 1, the 2, the 3, and the 4 in A. Then I have 2, 4, and 6 in B. So I hope you see this is B, and this is A. So what's the probability of A given that B happened? So given that B happened, you have 3, right? 3 out of 6. But the denominator, but yeah, so you know that B happened, so kind of you're saying this happened. So you only have 3 possible outcomes that you know happened. So that if A happened, knowing that B happened, it's 2 out of 3, right? So it's 2 out of 3. So I hope you see that this makes sense. And what I'm doing is basically this formula, right? E and F divided by E. I didn't write the probabilities, but it's just the numbers of 2 divided by 3. And if you write the probabilities, it would be dividing everything by 6, and it's the same thing. Okay, so conditional probabilities. If you have a table, it's pretty simple. You don't need the formula. If you have something like this, you might not need the formula. Sometimes you will need a formula. Now, the important thing about the formula is that it has this here, and we said that if E and F are independent, the probability of F given E is the same as the probability of F, right? So look what happens. If E and F are independent, it becomes the probability of E times the probability of F. So that's what it says over here. They are if the events are independent, so knowing that what happened does not affect the probability of the other, then the probability of E and F is the product of probabilities. My examples up here are if you throw a die twice, you get a 3 in the first throw and a 3 in the second throw. Well, you can think of it like it's the same example that we talked before about rolling 2 dice, and how many ways can you get a double 3? It's only one way up to 36, so it's 1 over 36. But I would have got the same if I did 1/6 for the chance of getting 3 in the first throw, 1/6 for getting 3 in the second throw, so it's 1 over 36. So I would get the same if I multiply, and that's because they're independent. The second time I throw the dice, it's independent from the first time I throw the die, and I can just multiply the probabilities. So now if the die is rolled and the coin is flipped, what's the probability that you get a 3 in the die and tails on the coin? Well, a 3 in the die is 1/6, a tails on the coin is 1/2, so you just get 1/12. So you would multiply the probabilities because the events are independent. So you have to be careful. This is only true if the events are independent. So what happens in the coin does not affect what happens with the die. That's why they're independent. Okay, let me see one last example here. So I'm going to assume, I'm sorry, I probably said on the top that I'm going to assume that the events, the next surgery is independent from the last surgery. So the probability of a particular knee surgery being successful is 0.85. I'm going to find a probability that 3 knee surgeries are successful. So I'm going to do this by saying, so the first one is simple, I guess. So if I assume that the second surgery being successful or not is independent from the first surgery being successful or not, independent from the third one, so this is going to be 0.85 for the first surgery, 0.85 by the second, and 0.85 for the third. And if you do those 3 multiplications, I think I have the number here. It should be 614. Now, if you find a probability that none of the 3 are successful, that means that they were all failures, right? So the probability that the first one was not successful was the complement of this 85, each one, so it's 0.15. But I also want the second one to not be successful, so it's 0.15. And I want the third one to not be successful, so 0.15. And if you do 15 to the third power, you get something close to 0.003. Now my third one says, find a probability that at least one is successful. Now this is one that sometimes we have trouble understanding what this says, but if at least one is successful, it's not the same as saying one was successful and 2 were not, because that would be exactly one successful. It says at least, so I need to find what's the probability of 1 successful, or 2 successfuls, or 3 successfuls. And the truth is that when it says exactly 1 successful, I have a little bit of a problem. It's not the same that the first one was successful or the second one. right? And it could have been the third one. So finding them this way would be a lot of work. I need to find 3 different probabilities. Well, we're going to get to that in the next chapter. But because it says at least one successful, it's going to be easy to say, this is, I'm going to write it down like the probability of at least one success is the same as the complement, so 1 minus the probability of all failures. Right? If it didn't happen that there were all failures, it means that at least one was a good one. So this is a lot easier than going into finding all possible ways that I could have had 1 or 2 or 3 successes. So I'm just saying it's a complement of this. And if you do that, of course you get 0.997. Okay, so this is called the multiplication rule, and use it when it's independent events, and you can use them in more than 2 if you do them in a row. Okay, so I think this is enough probably to go over the homework problems. Have fun with those.